Now let's look at luminescence. When electron hole pairs are generated in a semiconductor, or when carriers are excited into higher impurity levels from which they fall to their equilibrium states, light can be given off by the material. Now, many of the semiconductors are well suited for light emission, particularly the compound semiconductors with direct band gaps. The general property of light emission is called luminescence. Now, luminescence can be subdivided according to the excitation mechanism. If carriers are excited by photon absorption, the luminescence is called photoluminescence. Remember that photo means light. If the excited carriers are created by high energy electron bombardment of the material, then we call the luminescence cathodoluminescence. And if the excitation occurs by the introduction of current into the sample, we call that electroluminescence. So remember, this first part of the word refers to the excitation mechanism. Okay, so if you have your semiconductor here, you have your EC, and you have your EV. So when the electron is excited to the conduction band, so this is what we are talking about. This is the excitation mechanism. So this can be due to light, where we call it photoluminescence, when the electron now falls. So the luminescence part is when the electron falls back to the conduction band, giving off light with energy equal to Eg. So this is the luminescence part. And then this one is the excitation part. So if the excitation is due to light, we call that photoluminescence. If it is due to high energy electron bombardment, we call that cathodoluminescence. And if it is due to introduction of current into the sample, then we call that electroluminescence. Now, the simplest example of light emission from a semiconductor occurs for direct excitation and recombination of electron hole pairs. For steady state excitation, the recombination of electron hole pairs occurs at the same rate as the generation, and one photon is emitted for each photon absorbed. So here we now have a new phrase, steady state. Okay, so at thermal equilibrium, when you have no external excitation except for temperature, we call that condition the equilibrium condition. So this is the condition where you have no currents flowing in this semiconductor, for example. There is no net motion. The only thing that's generating electron hole pairs is heat or temperature. But now at steady state, you get excess carriers in addition to these equilibrium carrier concentrations. And if the total number of carriers, or the total number of electrons, for example, in the conduction band, if it remains constant with time, then you are in steady state. So we'll revisit this later in the following slides. And remember, here we are talking in terms of a direct excitation and direct recombination. Direct simply because the semiconductor is a direct gap semiconductor. Remember, if you plot your valence band and conduction band in K space, if the conduction band minimum and the valence band maximum are at the same K value, we say that the semiconductor is a direct gap semiconductor. And when you have a situation where you have something like that, where the conduction band minimum and the valence band maximum are at different K values, then we call that an indirect gap. And the process of recombination is a bit complicated because the electron falls back to the valence band via some states in the conduction band, so to speak. So we are saying when you have a direct recombination, that's the simplest example of light emission, and it's encouraged for you to understand at this early position that for emission of visible light, we usually expect or we usually get that from direct gap semiconductors only. So the direct gap semiconductors are the ones that usually result in emission of visible light, because the amount of energy is, all of it is transferred, is converted to light. So you have a direct recombination from the bottom of the conduction band to the top of the valence band, and the light that's emitted is equal to Eg. Remember, most semiconductors have band gaps between 1 electron volts and 3 electron volts. So this is basically the range of most semiconductors. So for you to have visible light emission, you require more or less a band-to-band recombination from conduction band to valence band. But if the recombination is from a mid-gap state somewhere, then the energy is going to be very small for it to be in the visible range. So you might get infrared or some other kinds of emission. But if you really want to have the emission of visible light, then you need a direct gap semiconductor. So for most optoelectronic devices, we usually use direct gap semiconductors because we can actually get emission of visible light when the electrons recombine with the holes in the valence band. Now, direct recombination is a fast process. The mean lifetime of the electron hole pair is usually on the order of 10 to the power minus 8 seconds or less. Thus, the emission of photons stops within approximately 10 to the power minus 8 seconds after the excitation is turned off. Such fast luminescent processes are often referred to as fluorescence. In some materials, however, emission continues for periods up to seconds or minutes after the excitation is removed, and these slow processes are called phosphorescence, and the materials are called phosphors. So, in summary, photoluminescence can be divided into fluorescence and phosphorescence. And the difference between these two is that when the emission stops approximately 10 to the power minus 8 seconds, we call that fluorescence. But when the emission continues seconds or even minutes after the emission, we call that phosphorescence. So this emission is very short, it stops quickly, but here it's kind of prolonged it lasts a little bit longer. So how can we make a semiconductor into a phosphor? How do we make phosphors? Because in both cases, these are all direct gap semiconductors. So what distinguishes a phosphorescence material from a fluorescence material? That's what we are going to look at in the following slides. So to make a phosphor, you usually require a defect level inside the gap. So to illustrate that, we have this example here. So this is an example of a direct gap semiconductor that contains a defect level, perhaps due to an impurity in the gap. So this is the level of the impurity, which we call ET. Now, because this state, this defect level, this impurity, has a tendency, a very strong tendency, to temporarily capture an electron, we call it a trap. So to simplify, if I have EC and EV in the state here, so if I have an electron there and the hole there, if the electron comes here and then re-excited again to the conduction band, comes back here, re-excited again, if this cycle repeats, then this state is a trap. So we have a trap energy level. We call that ET. This is a trap. So trap means temporarily capturing an electron. So it captures the electron and then it releases it. So if a state, if a state captures a carrier of one type, and the most probable next event is detrapping, then that state qualifies to be a trap state. Later on in the following slides, we are going to look at recombination sites, and then we'll clarify again the difference between these two. What distinguishes a trap state from a recombination center? So let's go back to our example here and try to understand what's going on. So in A, an incoming photon with h mu greater than Eg is absorbed. So the light is absorbed, and because your h mu is larger than Eg, the electron is going to be excited high up to the conduction band, and then the electron gives up energy to lattice scattering to the lattice by scattering until it nears the bottom of the conduction band. So the energy here is going to be lost as heat. And then when it reaches the bottom of the conduction band, the electron is trapped by this state here, right? And it remains trapped until it can be thermally re-excited to the conduction band. So it's trapped until it can be thermally re-excited to the conduction band. Now, when it is into the conduction band, two things can occur. It can also be trapped again by the same state and detrapped, trapped, and detrapped, trapped, and re-excited to the conduction band. This cycle can repeat itself many times, but eventually the electron will fall from the bottom of the conduction band to the valence band. And when it does so, it gives off a photon with energy equal to the band gap. So this is how you delay now the emission from something like 10 to the power minus 8 seconds to around seconds. So it is this process of trapping and detrapping that prolongs the process. So if the probability of re-excitation is low, then the delay is even longer. Or if the electron is retrapped several times before recombination, the delay becomes even longer. So to appreciate optical absorption, let's look at this photoluminescence example. Now in this example, we have a 0.4 micrometer thick sample of gallium arsenide. Remember, gallium arsenide is a direct gap semiconductor, which is illuminated with monochromatic light of energy 2 electron volts. The absorption coefficient alpha is 5 times 10 to the power 4 per centimeter, and the power incident on the sample is 10 milliwatts. So the first question is, find the total energy absorbed by the sample per second. And if you look at this figure here, what this means is the total amount of energy that is absorbed is, if you have your sample, this sample like this, and we have our incident light, which we can call in this case I0, and we have our transmitted light, which we are going to call here IT. So this is the intensity of the incident light, which in this case is 10 milliwatts. That's what's incident. So the intensity absorbed is going to be equal to incident minus transmitted. And then the intensity that is incident, we know that's 10 milliwatts, so we have to find this guy here. And it so happened that we have a formula for that. So remember, we derived IT, which was equal to I naught E to the power minus alpha L, where L was the thickness of the sample. So we can actually get the total energy absorbed by the sample per second, and this is greatly dependent now on the thickness of the sample. So we can do that. And then the second question is, find the rate of excess thermal energy given up by the electrons to the lattice before recombination. Remember that if you excite an electron into the conduction band, it loses its energy to the lattice through scattering mechanisms until it reaches the bottom of the conduction band. So we want to find this energy here. This one we want to calculate, and that's not going to be difficult at all. And then in C, it's asking us to find the number of photons per second given off from recombination events, assuming perfect quantum efficiency. So we'll look at what perfect quantum efficiency really means. So to answer part A, we use our equation. The intensity of the transmitted light is equal to the intensity incident on the sample times E to the power minus alpha L, where alpha is the absorption coefficient, which is also given in this case, and L is the thickness, which is also given. So if you plug in the values, you'll find your answer to be 1 milliwatt. So the power that is absorbed is now the incident minus the transmitted, which gives us 9 milliwatts. And 9 milliwatts is equal to 9 times 10 to the power minus 3 joules per second. Now the second question asks the fraction, the amount of energy that is converted to heat per second. So to do that, we start by calculating the fraction of each photon energy unit which is converted to heat. And to do that, we simply say that we have 2 electron volts incident, but the one that is absorbed is the one that is going to be emitted is 1.43. So this is the gap, the EG, the energy gap. So you have your EC and you have your EV. This gap is 1.43. So you've got your electron goes there and it's lost. So to get this amount, we can simply say 2 minus the gap, 1.43. And to get the fraction of each energy unit, then we divide again by 2 because we have 2 incoming. So it's 2 electron volts, which is the incident, and then we have electron volts. So we have 2. This is a fraction, so it's 2 minus 1.43 divided by 2. So because we want the fraction of these 2 electron volts. So we get 0.285, and thus the amount of energy converted to heat per second is equal to the amount of energy that is absorbed times that fraction now. So this is the total amount absorbed, but the ones that's converted to heat is the remaining, is this fraction that we have calculated here, 0.285. So we simply multiply that and we get 2.57 times 10 to the power minus 3 joules per second. Now to the part C now, it asks us to assume perfect quantum efficiency. So by perfect quantum efficiency, we assume that one emitted photon energy for each photon absorbed. So we don't have any losses. So we emit 1 light per every photon absorbed. So we emit 1 photon per every photon absorbed. And remember, the photon absorbed and the photon that is emitted are different, right? The photon that is absorbed has h mu greater than Eg, but so this is absorbed. But the photon that is emitted has h mu equal to Eg. This one is the emitted one. Okay, so always keep that in mind. So we absorb anything that's larger than Eg, but we always emit equal to Eg. So if we assume perfect quantum efficiency, what we simply do is we now convert our energy to electron volts, and then we multiply by our the amount of energy then we divide by the amount of energy that every photon gives. So this will give us the, if I can take you back, this will actually give us the amount of energy, the number of photons that is emitted per second. So if you do that, you get your 9 times 10 to the power minus 3. So this is the total energy that is absorbed, and then you divide this by 2 electron volts per photon, because each photon gives you 2 electron volts. And for you to have a good comparison between electron volts and this joules per second, you have to convert your joules here to electron volts by dividing by 1 times 6 times 10 to the power minus 19. So if you do this, you get 2.81 times 10 to the 16 photons per second. Another alternative is to consider the amount of light that is emitted. So so this is 9. This is the total amount absorbed, and then 2.53 is the one that is lost to the lattice due to scattering, and we are only going to emit 6.43. So because we are now considering only the emitted light, we don't use 2 electron volts in this case, but we use 1.43 electron volts, which is the energy gap. So it's either method is correct. Okay. So electroluminescence is what we are going to cover in chapter 5, where the excitation mechanism is now the application of current to the semiconductor. So in LEDs, which means light emitting diodes, an electric current causes the injection of minority carriers into regions of the crystal where they can recombine with majority carriers, resulting in the emission of recombination radiation. So in photoluminescence, you shine light to create electron hole pairs or to create excess carriers, but in electroluminescence, you actually use light to current to inject carriers into the semiconductor. So this important effect, injection electroluminescence, will be discussed later in chapter 5. Now let's look at carrier lifetime and photoconductivity. When excess electrons and holes are created in a semiconductor, there is a corresponding increase in the conductivity of the sample, as indicated by this equation here. So in simple terms, we know that our Jx is proportional or is equal to lambda Ex. So if the current density, the total current density, is proportional to the electric field, and the constant of proportionality is the conductivity. Now this conductivity here is equal to Q n mu n plus P mu P. So you can see that if either the electron concentration or the hole concentration, or if both the N and P, if they go up, then our conductivity also goes up. So if we are saying that excess carriers are in addition to the equilibrium carrier concentration, it means that in the presence of excess carriers, our N will increase, because N is equal to N naught, which is the equilibrium carrier concentration, plus a delta N, for example. So P is equals to P naught plus a delta P. So the delta here, the delta N, the delta P, these are the excess carriers. The excess carriers. So because the total number of electrons and holes increase in the presence of excess carriers, the conductivity will also increase. I think that's straightforward. So if the excess carriers arise from optical luminescence, the resulting increase in conductivity is called photoconductivity. Now in this section, we shall examine the mechanisms by which excess electrons and holes are recombined. Now let's try to understand what direct recombination is all about. Now before we go into the definition of terms, let's see the situation that we are considering here. So if we have a semiconductor, we are saying that at thermal equilibrium, the recombination equals generation, such that you have a constant number of electrons and a constant number of holes. Electrons in the conduction band and holes in the valence band. So this is what happens at thermal equilibrium. Now, if you shine light to this sample, you increase now the number of carriers in the conduction band and valence band. Now the number of electrons becomes n naught plus delta n, where delta n is the excess electron concentration, and then the whole concentration increases to p naught plus delta p. So this becomes your new electron concentration and your whole concentration. Now, if you remove this light, you will find that the number of electrons is going to decrease. It's going to decay. So we are saying this will decrease, it will decay. That's the word we are going to use. It's going to decrease or decay. Same applies to the number of electrons. It's going to decrease or decay with time, because you no longer have light. So the number of equilibrium carrier concentrations is going to remain constant, but what's going to actually decay are these excess carrier concentrations. Remember that when you turn off the light, so we are saying you turn off the light, but you still have temperature, but still have temperature. So when you turn off the light, you have thermal generation without optical generation. So let me just clarify here. So when light is on, you have optical generation plus thermal generation. And when you turn off the light, when light is off, you are only left with thermal generation. So the total number of electrons and holes is going to decrease. It's going to decay with time. So when we say direct recombination, in this case, we are considering the decay of electrons and holes after turning off the excitation, after turning off the light. We want to see how the concentration of electrons and holes decreases with time. That's what we are talking when we are talking about when we say excess carrier lifetime, or when we talk about direct recombination. We are saying this in the context of excess carriers decaying after the excitation is removed or the excitation is turned off. Okay, so we are saying that excess population of electrons and holes decay by electrons falling from the conduction band to empty states in the valence band. Now, energy lost by an electron in making the transition is given up as a photon. So direct recombination occurs spontaneously, which means that probability of electron and hole recombination is constant in time. Okay, and the decay of electrons and any time t is proportional to the number of electrons and holes remaining at time t. So this is very, very important. So we are saying the decrease of electrons and holes, that's the decrease, is always proportional to the number of electrons at time t and holes at time t. It's proportional to both, so we multiply. Okay, and then when we remove this constant, this proportionality sign, we put a constant of proportionality alpha r, like that. So this alpha r is the recombination constant, the coefficient or the constant of proportionality for recombination. Now we know the rate of decay. So when we now consider the net rate of change of electron concentration, we should add thermal generation. Remember that when you turn off the light, you still have the thermal generation. So the net rate of change of conduction band electron concentration is going to be equal to the thermal generation rate minus the recombination rate. So this is the recombination rate, and to that you add the thermal generation rate. Now, if you suppose that excess electron hole population is created at time t equals to 0, so this is immediately it's just before you turn off the light. For example, by a short flight of light, we can assume the following. The initial excess electron and hole concentrations are equal. So this makes sense because electrons and holes, they occur in pairs. You have electron hole pairs when you shine light. So the initial excess electron and hole concentrations, which we represent here by capital letter delta. So we have delta N and delta P. These are equal. And the reason is because electrons and holes, and because electron and holes combine in pairs, the instantaneous concentrations of excess carriers are also equal. So at a time t, which is greater than 0, we represent the excess electron and hole concentrations with small letter delta, a symbol. So we put t, simply means it's a function of time. So this delta, this is the excess electron carrier concentration at time t, and we'll have delta p t, like that. But in most cases, when we write these, we can remove the t. We can it's also still okay not to show the t, just for simplicity. So we are saying the initial excess electron concentration, delta N and delta P are equal, because that's obvious. Electron and hole occurs in pairs. Electron and holes, they occur in pairs. And when the electron and hole, because the electrons and holes combine in pairs, also the instantaneous concentrations of excess carriers are also equal. But I should add that assuming no trapping, because once you have trapping, then it's a different case altogether. Remember, when you have trapping, you trap an electron, it stays there, and then it's re-excited. So the time that the electron is going to be trapped this time, it means you now have less electrons than holes. So delta N and delta P are not going to be the same when there is trapping involved. So if you have no trapping, yes, you can say that these two are going to be equal. And one other thing is, remember we said our delta N T dt was equal to something. Now, if you consider the conduction band electron concentration, the decrease in the net change in the conduction band electron concentration, you will find that the rate of the net rate of the change of the conduction band electron concentration is equal to the rate of the change of excess electron concentration, because it is the excess carriers that actually decrease in concentration, not that and that corresponds to a total decrease in the electron concentration. So what I'm just trying to say is that dNt dt is equal, the net rate change of the total electron concentration is equal to the net rate change of the excess electron concentration, because it is the excess carrier concentration that actually change with time. So this is equal to that, and you remember our dNt was equal to the generation rate minus the recombination rate, and for the recombination rate we had n, so the total number of electrons is equal to the equilibrium concentration plus the excess electron concentration. The same applies to the Hall concentration. It's equal to the equilibrium Hall concentration plus the excess Hall concentration. Now if you expand the brackets, you get this term there. Now before we get the solution for this, we have to simplify this solution further, and to do that we assume two things. So the first thing that we are going to assume is that the material is extrinsic. So when the material is extrinsic, it means that for a p-type material, P is going to be much larger than Ni and much larger than N for an extrinsic material. And for a N-type material, it's going to be vice versa. So N is going to be much larger than P for an extrinsic material. Now, the other thing that we are going to assume is what we call low-level injection. So low-level injection means for an p-type material, material, delta N is much smaller than P naught, and for a N-type material, delta P is much smaller than N. So we are going to assume these two conditions: the condition of an extrinsic material where the majority carriers are much larger than the minority carriers, and we are also going to assume low-level injection where the excess carrier concentration is much smaller than the majority carrier concentration. So if we assume that, you will find that for the case of a p-type material, so this is the case of a p-type material, you will find that, come in. So by assuming low-level injection and an extrinsic material, you can see that in this equation here we can get rid of delta sigma naught. So we are saying we have P naught, so this is a p-type material. P naught is much greater than delta N. So because of this, delta N, P naught is much greater than delta N, delta N. So we can, in this case, delta N squared, we can get rid of that. And another thing is we can also get rid of N naught, because in an extrinsic material, P naught is much greater than N naught, so this one can go. If we do that, we get a much simplified equation. Now in this equation, we are taking a differential and we get the same function plus a constant. So in this case, the solution is exponential, and it's an exponential decay from the initial excess electron concentration. Now our alpha tau p naught, if we say that this is equal to tau n, so if our tau n is equals to 1 over alpha tau p naught, then we can actually rewrite our instantaneous electron concentration as delta n e to the power minus t over alpha n. So the electron carrier concentration decays with t from the initial excess electron concentration through this relationship. Okay, so excess electrons in a p-type semiconductor recombine with a decay constant tau n, which is equal to 1 over alpha r p naught. And since the calculation is made in terms of minority carriers, remember that we are considering a p-type semiconductor where electrons are minority carriers. So this term is made in terms of minority carriers. So since it is made in terms of minority carriers, it is often called the minority carrier lifetime. Our tau n is the minority carrier lifetime. So what this means is if you inject electrons in a p-type semiconductor, they will last tau n seconds, for example, before they recombine. That's the lifetime. That's the amount of time that they can spend in the semiconductor before they recombine. Now, the decay of excess holes in an n-type semiconductor occurs with the rate tau p, which is equals to alpha r n naught. So you simply change your p with n and your p naught with n naught. So in the case of direct recombination, the excess majority carriers decay at exactly the same rate as the minority carriers. A general expression for low-level injection is tau n, which is equal to alpha n naught plus p naught. So this is true for low-level injection and no trapping. Okay, now this example clearly shows what we are talking about when we say excess carrier lifetime, because it shows the decay of excess carriers in a semiconductor with time. So in the example, we have a sample of gallium arsenide which is doped with 10 to the 15 acceptors per cubic centimeter, and the intrinsic carrier concentration of gallium arsenide is 10 to the 6 electron hole pairs per cubic centimeters. Thus, the minority electron concentration is going to be equal to Ni squared divided by P naught, which is 10 to the power minus 3. So this is the law of mass action. So certainly the approximation that P naught is much greater than N naught is valid in this case. You can see that P naught, which is 10 to the 15, is much greater than 10 to the power minus 3. So the intrinsic condition is satisfied in this example. Now, if 10 to the 14 electron hole pairs are created at t equals to 0, we can calculate the delay of these carriers in time. So the approximation that the delta N should be much less than P naught is also satisfied because there's an order of magnitude difference. Remember, in this case, your delta N is 10 to the 14 and your P naught is 10 to the 15. So indeed, P naught is much greater than delta N. Now, figure 4.7 shows now the decay in time of excess populations for a carrier recombination lifetime of 10 to the power minus 8 seconds. So we can see that if we have excess carriers, the whole concentration is not going to increase much, because it's just going to be 10 to the 15 plus 10 to the 14, which is equals to 1.1 times 10 to the 15. So there's a slight increase. So at t is equals to 0, you're going to have this amount of whole concentration, and the whole concentration will slightly decrease with time to the equilibrium carrier concentration. Now, what's very interesting to note here is that the case is very different for minority carriers in this case, which are electrons. Remember, this is a p-type semiconductor. The electron carrier concentration starts at 10 to the 14 because you have injected 10 to the 14 electron hole pairs. So you get 10 to the 14 electrons at t is equals to 0, but these should decay very fast to around 10 to the power minus 3. Remember, 10 to the power minus 3 is the equilibrium electron concentration. So you have a very large gradient in this case. The difference in carrier concentration, the gradient here is very, very, very steep for minority carriers as compared to the gradient or the change in the majority carrier concentration. So we are now saying here that the large percentage change in the minority carrier concentration and the small percentage change in the majority carrier concentration is quite notable in this example. Now, as you see later on, this is going to be important when we look at diffusion current, where you will find that in the presence of excess carriers, it is actually the minority carriers that contribute the most to diffusion current than the majority carriers, because you always have a large gradient in the concentration of minority carriers than the concentration of majority carriers in the presence of excess carriers. Now, in indirect semiconductors such as silicon, where you have the conduction band minimum and the valence band maximum at a different K value, the situation is different. So the vast majority of recombination events in indirect materials occur via recombination levels within the band gap, and the resulting energy loss by recombining electrons is usually given up to the lattice as heat rather than emission of the photon. Now, an impurity lattice defect can serve as a recombination center if it is capable of receiving a carrier of one type and subsequently capturing the opposite type of carrier, thereby annihilating the pair. So if you look at this example here, you can actually understand what a recombination center does. So in this case, the recombination center that we have is ER here. Now, ER is below EF, so means that ER is going to be filled at equilibrium. It's a recombination center. This is actually a state. So the state is going to be filled at thermal equilibrium because it is below EF. Right? So the first event in the recombination process is going to be hole capture. So because this guy is filled, so we are going to capture a hole to that place there. So the place captures a hole. Remember that hole capture is similar to an electron falling to the valence band. That's hole capture. And yes, we have holes in the valence band because this is not 0 kelvins. It's at some temperature, let's say 300 kelvins. So we are going to have lots of holes in the valence band. So the first step is hole capture. A hole is going to be captured by this state, or in other words, an electron is going to fall to the valence band from this state, but let's call it hole capture. So the first event in the combination process is hole capture, which is equivalent to an electron falling at ER to EV, leaving behind an empty state at ER. Thus in hole capture, energy is given up as heat to the lattice because an electron falls down, so energy is given up as heat to the lattice. Similarly, energy is given up when a conduction band electron subsequently falls to the empty state in ER. So after you create an empty state, an electron is going to fall again to the empty state in ER, and again heat is going to be given off rather than emitting light. So when both these events have occurred, the recombination center is back to its original state, filled with an electron, but an electron hole pair is missing because you lose an electron and a hole here. This becomes an electron, a recombination center. So now, how do you actually now distinguish between a recombination center and a trap? So when a carrier is trapped temporarily at a center and then re-excited without recombination taking place, the process is often called temporary trapping. An impurity or defect center is referred to as a trapping center or simply a trap. If after capturing one type of carrier, the most probable next event is re-excitation. So what we are saying is, if you have your EC and your EV and you have a state here, let's call it ET. If it captures an electron, and this is event number 1, and the next most probable event is re-excitation, event number 2, then this state qualifies to be called a trap. But if, for example, we have a state that is here, if we have this case, if this state captures a hole and then the next step is capturing an electron, then this state is called a recombination center. So if we use this definition, you can see that a trap is a state that after capturing a carrier of one type, the most probable next event is re-excitation, whereas a recombination center captures a state of one type, and the next most probable event is the capture of a carrier of the other type. So if a state captures an electron and the next state is capturing a hole, or vice versa, if it starts by capturing a hole and then it captures an electron, then it becomes a recombination center. But if it captures an electron and re-excites the electron, captures the electron and re-excites the electron, it becomes a trap. Or if it captures a hole and re-excites the hole, captures the hole and re-excites the hole, it's also a trap state. Now, from this, you can see that when states are close to the conduction band, they are most likely to act as electron traps. Why? Because it requires less energy. So if an electron falls to this state, it's much easier to re-excite it because you need less energy to re-excite the electron than after capturing an electron, you require a lot of energy to capture a hole in that case. So in this case, it's the trap. It's when a state is close to the conduction band or when it's close to the valence band, the state is most likely to be a trap because it's easier to capture. In this case, if it captures the hole, it's easier to re-excite the hole than to capture a hole and then capture an electron because you need a lot of energy to do that. So states that are close to the conduction band are usually electron traps, and states that are close to the valence band are usually hole traps. Now, when a state is mid-gap, you can see that there is 50% chance of being able to capture an electron and then capture a hole. So when states are mid-gap, they are most likely to play the role of recombination centers because the energy that is needed to capture a carrier of either type is more or less the same. So we are saying in general, trap levels located deep in the gap are slower in releasing trapped carriers than the levels located near the band gaps. This is because more energy is required to re-excite a trapped electron from a center near EI than required to re-excite an electron from a level close to EI. So what this simply means is if you have two traps, for example, tin here and sulfur here, and tin is going to be much faster at releasing the trapped electron than sulfur because you need less energy to re-excite the electron in the case of tin compared to sulfur. So another important experiment in optoelectronics is the photoconductive decay experiment. So this actually measures the photoconductivity of a sample. Remember, if you shine light, the conductivity increases, and the increase in conductivity is called photoconductivity. So the way we measure the photoconductivity is shown here. So you get a flashlight or a monochromator that generates light, or you get a flash generator and you get a filter or a monochromator of some sort, something that just passes through only the light of a specific wavelength that you want, and then you shine that light on a sample, and then you can actually measure the voltage across the sample. You can see that when there is no light, the voltage is going to be very high, but when you pass light, you get a lower voltage, and when you turn off the light, the voltage will decay, will start rising again to match the initial condition. So this is how you measure the photoconductivity. So we are saying the effects of recombination and trapping can be measured by the photoconductive decay experiment. The conductivity of the sample during the decay is given by that. And remember, this guy is going to decay exponentially after you turn off the light. So the conductivity will also decay exponentially. So if I have to plot here the conductivity instead of the voltage, if I have that, then I'll get a conductivity here, and if I turn on light, the conductivity will jump, and if I turn off the light, then the conductivity will decrease like that. Okay, and we are saying that the conductivity without light illumination, we call this the dark conductivity, because it is the conductivity of the sample in the dark. And this increase in conductivity, this increase here after turning on the light, is what we call the photoconductivity. So the effects of recombination now can actually be seen. The rate of decay. This rate of decay, you can actually see it now by using this experiment. By this experiment, you can actually see the rate. Now, it's very important to clearly understand the difference between equilibrium and steady state. Now, the term equilibrium refers to a condition of no external excitation except for temperature and no net motion of charge. So this is just the semiconductor lying there without having any electric fields being applied to it. It's in the dark, and the only thing that's generating electron hole pairs is temperature. That's what we call equilibrium. So an example is a sample at constant temperature in the dark with no fields applied. And in that case, thermal generation, which is equal to alpha R Ni squared, is equals to alpha R N naught squared. And this one is also equal to the recombination rate. So you may have a constant number of carriers at any given time in the conduction band. Now, the term steady state now refers to a non-equilibrium condition in which all processes are constant and are balanced by opposing processes. So, for example, a sample with a constant current or a constant optical generation of electron hole pairs just balanced by a recombination. So you now get a constant current or a constant optical generation of electron hole pairs that's just balanced by recombination. So that's what we call now a steady state. So you do have a current, but the current is constant. Now let's look at steady state carrier generation. So at steady state, in addition to optical generation, or in addition to thermal generation, you also have optical generation. And this is equal to alpha R N P. You can notice here that we have removed the knots. We are not saying N naught, P naught anymore, because we are no longer at thermal equilibrium. And the total number of electrons is equal to the equilibrium electron concentration plus the excess electron concentration. The same applies to the total number of holes, which is equal to the equilibrium hole concentration plus the excess hole concentration. Now, remember that for steady state and no trapping, the excess carrier concentrations are equal. They decay at the same rate as I explained before. So now if you expand the brackets, if you remove the brackets and expand this expression, you get to that point. And since the term alpha N naught P naught, this guy here, is simply the thermal generation rate, and this guy here can be removed for low level injection. Remember, for a P type material, delta N is much greater than N delta N, because P naught is much greater than delta N. So we can get rid of that, and if you do that, you'll find that your So if this guy is GOT, the GTs, if this is the thermal generation rate, this guy goes and that guy also goes. And if this guy goes, everything is simplified to that, which is equal to that. So we can now express our excess carrier concentration in terms of the optical generation rate and the minority carrier lifetime. So this is a very cool equation. So we can do this, but when we have trapping where tau p and tau n are not equal, then we have to consider these guys separately. So the excess electron concentration is going to be equal to the minority carrier concentration times the optical generation rate. And for holes, we are going to have a different thing like that. Another important thing is the concept of quasi-Fermi levels. So you'll find that the Fermi level, EF, is meaningful only when no excess carriers are present. So for steady state electron concentration, we define quasi-Fermi levels, Fn and Fp, for electrons and holes respectively. And the resulting carrier equations are very simple. It's simply, you remember, for N, we had Ni, E, then we had EF minus EI over KT, and for P it was the same thing. We had Ni, E, then EI minus EF over KT. So you simply take these equations and substitute EF for Fn for electrons and EF for Fp for holes. And this example actually shows you now how to calculate the quasi-Fermi levels. So in this example, we are going to assume that 10 to the power minus 3 electron hole pairs are created optically every second in silicon sample with N naught equal to 10 to the 14 per cubic centimeter, and the minority carrier, the minority lifetime is equal to 2 microseconds. So the steady state excess electron or hole concentration is then given by delta N, which is equal to delta P, is equal to the optical generation rate plus tau times tau N, the equation that we just derived in the previous slide, which is equal to that. So while the percentage change in the majority electron concentration is small, the minority carrier concentration changes from, you can see that P naught was equal to Ni squared divided by N naught, which is equal to 2.2 times 10 to the power 6. But now if you have generation of 2 times 10 to the power 13 electrons and hole pairs, then you can see that the concentration of minority carriers changes significantly. There's a big change from 2.25 times 10 to the 6 to 2 times 10 to the power minus 13 at steady state. So note that the equilibrium equation N naught P naught equal to Ni squared cannot be used with the superscripts removed. That is, N naught P naught is not equal to Ni squared when excess carriers are present. So what we learn from here is that the majority carrier concentration does not change a lot, because in this case the majority carrier concentration simply changes from 1 times 10 to the 14 to 1.1 times 10 to the 14. Okay, that's a very slight change. Whereas my minority carriers change from 10 to the 6 to 10 to the 13. more than 7 orders of magnitude, around 7 orders of magnitude increase. Okay. So the steady state electron concentration is going to be equal to n naught, n which is equal to n naught plus delta n, which is equal to 1.2 times 10 to the 14, which is equal to that from our equation, n equals to ni e f n minus ei over kt. So from this equation, the one we just looked at in the previous slides, so if you do this, you will find that f minus nei is around 0.233 electron volts, and f minus ei is going to be equal to 0.228 electron volts. So what we can see from here is that for an n-type semiconductor, it's very clear that the quasi-Fermi level of majority carriers for an n-type or p-type, the quasi-Fermi level of the majority carriers is very close to the Fermi level, to the Fermi level, or to the equilibrium Fermi level, whereas the quasi-Fermi level of the majority of the minority carrier concentration is very different from the equilibrium Fermi level. So you'll find that the gap, this one Fn minus Fp, kind of gives you the measure of the excess electrons that you have in the sample. So we said that in the presence of excess carriers, the conductivity increases, and this increase in conductivity is called photoconductivity. So in other words, we get a change in resistance when the sample is exposed to light. So the resistance actually decreases. Remember, in the previous slide, we looked at the voltage was going to decrease and then later on increase. So in the presence of light, the resistance, the voltage decreases. So if voltage decrease means the resistance is decreased. So the resistance, which is equal to voltage over current. So if V decreases, the resistance is also going to decrease. So some photoconductors respond from impurity levels, so photons less than the band gap energy can actually result in the decrease in sensitivity. So it's just important to note that in some cases we have ECV. So if the gap is clean, we only need to have H mil, which is greater than EG. But if you have states in the gap, then even H mil less than EG can actually result in absorption, because an electron can be absorbed here and go there, or an electron can be excited from a state to the conduction band. So you can see that if you have states inside the gap, H mu less than EG can actually result in a photo excitation. So now the optical sensitivity is related to the optical generation rate by this equation here. Remember, we derived this, that the excess carrier concentration is equal to tau n times GOP for electrons, and the excess O concentration is equal to tau p times GOP. So the photoconductivity change, the increase in the photoconductivity, which is equal to Q. So remember, your sigma is actually equal to Q Q brackets, you have N mu n plus p mu p, like that. And we are saying that the photoconductivity changed due to excess carrier concentration. So my delta, this is going to be equal to Q, and then I have sigma n mu n plus sigma p mu p. This is the photoconductivity, the increase in conductivity due to illumination. So the increase in photoconductivity is going to be equal to that, and we know that our delta n is equal to tau n g or p. So if you see this, you'll find that the increase here is equal to that if you consider both electrons and holes. So you'll find that the mu tau product, the mobility carrier lifetime product, the mu tau, the product of these two, is very, very, very important when we analyze photoconductive devices. So the larger the products are, if mu tau is large, then you get a larger increase in conductivity. So your device is more sensitive to light. It has a more optical sensitivity if tau and n are large. So large carrier mobility is important, and long lifetime. So you need large mobilities and long lifetime for you to have large sensitivity, large optical sensitivity. Now, to achieve this large optical sensitivity, there's always now a compromise now between sensitivity and response time and dark resistance. So remember, the dark photoconductivity is the photoconductivity of the sample in the dark. So sometimes when you want to have larger photosensitivity, you have to increase the mobilities. So sometimes to do that, you need to use short channel TFTs, but this can result in very large off currents and other non-ideal behavior. So there's always a compromise between getting large sensitivity and the dark resistance of the stability of the device.